Hello, welcome to lecture 19 of the course. In the last lecture, we have learned that when quantized, an electromagnetic radiation can be or light can be treated as a stream of photons, and each photon behaves like an independent harmonic oscillator. In this lecture, we are going to learn about the statistical properties of light, and we will see the consequence of treating electromagnetic radiation or light as a stream of photons. In the last class, we have learned that when quantized, each mode of the electromagnetic field or light behaves like a harmonic oscillator. Now, the quanta of the electromagnetic field or light is called a photon. However, there is a subtle difference between the nature of the photon for the case of a propagating electromagnetic field and a standing electromagnetic field. In the case of the propagating electromagnetic field, the photon has a definite momentum and a definite energy, but for the case of the standing electromagnetic field, when quantized, it behaves again like a harmonic oscillator, but the quanta of the standing electromagnetic field, which is again termed as photon, the average momentum of the photon is zero. That means that when we make a measurement of the momentum of the photon, then either we get plus s cross k or minus s cross k, because the standing wave is formed by the superposition of a forward propagating wave and a backward propagating wave, and the photon has a definite energy, which the energy is h bar omega. Now, for the propagating electromagnetic field, we have also worked out how the electric field operator can be written in terms of the so-called annihilation and the creation operator. And also for the case of the standing wave, we have written the operator for the electric field, and also we have worked out the operator for the magnetic field, vector potential, and so on can be worked out. And ultimately what we found that the photon behaves like a harmonic oscillator. So when quantized, so this is the key result, that when quantized, an electromagnetic field behaves like a harmonic oscillator, and its Hamiltonian is exactly looks like the so-called linear harmonic oscillator Hamiltonian that we encounter in a quantum mechanics course. Okay. In this lecture, however, we are going to discuss photon statistics, and to this end, we are going to consider the detection of light beam by a photon counter as it is illustrated in this figure here. So what you see here, that a low intensity light is getting incident on a photomultiplier tube called PMT in short, or avalanche photodiode, or called APD, which is again connected to a electronic counter, and this detector produces short voltage pulses in response to the light beam, and the counter register the number of pulses emitted within a time interval which is set by the experimentalist. So here you see in the output, you see these spikes here, the number of pulses in terms of the basically the voltage. This represents the voltage actually, this whatever the spikes you are, these are the counts. Now let's say the time interval that is set by the experimenter is capital T, and for simplicity let us consider the detection of a perfectly monochromatic beam of light which has an angular frequency omega, and it has a constant intensity I, it has a power P, and the cross-sectional area of the beam is A. Then the photon flux, which is denoted by this symbol phi, can be defined as the average number of photons passing through the cross-section in unit time. So this can also be expressed as the ratio of energy flux to energy of the individual photon, and energy of the individual photon, you know, that is h bar omega, and energy flux, that's the energy, total energy,
is I into A. I is the intensity, A is the area, and this also can be written in terms of power divided by h bar omega, because I into A is power, because power is energy per unit time and intensity is energy per unit time per unit area, so I into A is power, right? And photon flux is simply P by h bar omega. Now each detector is characterized by the quantum efficiency eta, and this is defined as the number of photo counts. It's a ratio, it's a number, it's the ratio of the number of photo counts to the number of incident photons. Now, therefore, the average number of counts registered by the detector in a counting time t, which the experimentalist has already said that the counting time is capital T. So the average number of counts registered by the detector in time capital T is, this is the average number n of t, which you can work out simply by multiplying the quantum efficiency with the photon flux and the time interval t. Then you get this formula for the average number of counts, and therefore the count rate, average count rate, is going to be average number of counts per unit time. So that is your capital R. I think these are very easy to understand. So count rate formula, average count rate formula is eta P by h bar omega. So this is the formula you can use, where eta is the quantum efficiency, P is the power, S cross omega is the energy of the individual photon, right? So however, there is an important point to note. The maximum count one can have is usually determined by the fact that the detectors need a certain amount of time to recover after each detection count. So suppose the detector is counting certain number of photons, then again for the next count it has to have some kind of a dead time, right, so that it can operate effectively, and this time is generally on the order of 1 microsecond. Okay, so what I mean to say is that in general a time on the order of 1 microsecond must elapse between successive counts, and this sets the practical upper limit of this maximum number of counter or average count rate R to be around 10 to the power 6 counts per second. A typical photo counter is only useful for analyzing properties of very faint light beam of optical power on the order of 10 to the power minus 12 watt or less. For detecting light beams of higher power, different methods needs to be used. Now, one thing you should note, that a beam of light with well-defined average flux will show photon number fluctuation at short time intervals. So let me reiterate this once again. A beam of light with well-defined average photon flux will show photon number fluctuations at short time intervals. To appreciate it, let us consider an example. Let's consider a beam of light which is a photon energy 2 electron volt and average power say 1 nanowatt. Okay, then the photon flux can be easily calculated, because you know the power and you know the individual photon energy which is 2 electron volt, and then if you put the values, then you are going to get that the photon flux is going to be 3.1 into 10 to the power 9 photons per second. Now you know that the speed of light or the velocity of light c is equal to 3 into 10 to the power 8 meter per second. This means that the length segment of the beam, say length of 3 into 10 to the power 8 meter, contains, in our given problem, contains 3.1 into 10 to the power 9 photons. This I am saying in the context of the given problem. So this implies that a beam segment
of length, if I take a short length, say 3 meter, if the beam segment has length 3 meter, then it's going to contain, it's easy to calculate, it would be 3.1 into 10 to the power 9 divided by 3 into 10 to the power 8. That's the number of photons per unit length. Okay, because I think this maths is very easy. So 3 meter length is going to contain, if you do the calculation, you will see that 31 photons is going to be contained by that segment of beam segment having length 3 meter. As we go on considering shorter length segment, we will find that the average number of photon becomes fractional. So far we are considering the count time to be 1 second, right, here. Now suppose the count time is 1 nanosecond. Say the count time is equal to 1 nanosecond, that is 10 to the power minus 9 second. Then this means that the corresponding length of the beam segment, you can make it out yourself, it's very easy. Segment is going to be equal to 30 centimeter. Let me explain. You see that 1 second corresponds to a length of 3 into 10 to the power 8 meter. So this means that 10 to the power minus 9 second is going to correspond 3 into 10 to the power 8 into 10 to the power minus 9 meter, which is equal to 3 into 10 to the power minus 1 meter, and which is 30 centimeter. So I hope you get the idea. Now we saw that 3 meter or 300 centimeter, right, corresponds to which is the length of the beam segment. This beam segment contains 31 photons, right? So which means that 30 centimeter of the beam segment, these are very elementary maths. Beam segment has how many number of photons? You are going to get 31 divided by 300 into 30. So this is going to give you 3.1 photons. So as you go on decreasing the length of the beam segment, you see the average number of photons is also getting reduced. By the way, 3.1 is the average number only, and because photons are discrete energy packets, the actual number has to be integer. So if we are now having a beam segment of length 30 centimeter, on the average it's going to contain 3 photons. Now note that these 2 electron volt light beam that we are considering, that correspond to a beam of light at 633 nanometer wavelength. Let me explain. You see, the photon in the beam has energy 2 electron volt, so wavelength is going to be Sc by E, right? I hope you know this formula, that energy is equal to hc divided by lambda. So from there I had lambda is equal to hc by lambda, where h is the Planck's constant, which has the value 6.626 into 10 to the power minus 34 joule second. C is 3 into 10 to the power 8 meter per second, and energy of the photon is 2 electron volt. In terms of joule, I can write it as 2 into 1.6 into 10 to the power minus 19. So if you do the maths, you are going to get the wavelength of the beam to be around 633 nanometer. So here that means the 30 centimeter section of the beam light at 633 nanometer with a power of 1 nanowatt contains 3 photons on average. Now if we assume that the photons are equally likely to be at any point within the beam, then it can be shown that we will going to find the random fluctuations above and below the mean value. So this statement is very important, and we are later on going to show this, establish this, that the random fluctuation of photon numbers is going to be, will lie above or below the mean value. Now, say for example, let me explain it further. Say for example, if we were to look at 10 such segments of the beam, so which each of the segment is having length 30 centimeter, and then if we find we may actually find a sequence of photon counts that is going to look something like this, where you see this particular segment has number of photon is 4, here it is 3, 6, 4, 2. In total we are having 10 segments, so distribution would be like this. Now if you sum the number, and it's going to give you, sum is going to be 32, and this implies that mean is going to be 3.2. So I hope you are getting the idea. You know, the statistical fluctuation here arise due to the fact that we do not know exactly where the photons are within the beam. Now let me explain it further. Suppose if we make the length segment of the beam even smaller, the fluctuation is going to become even more apparent. Let us say the beam segment now has a length 3 centimeter. In the earlier case we are taking in this here 30 centimeter. Now let us take the beam segment to be having length 3 centimeter, which corresponds to a time interval of 100 picosecond, and you will find that the average number of photon is equal to just 0.31. Let me explain it again, explain the maths actually. You see again that 3 into 10 to the power 8 meter of length segment is going to have number of photons that we have calculated is 3.1 into 10 to the power 9 photons per second, right? That's what we have already calculated in our given problem. So this implies that 100 picosecond corresponds to length. This corresponds to length 3 into 10 to the power 8 meter per second into 100 picosecond, and you know picosecond is 10 to the power minus 12. So if you again do the maths, you are going to get that this length is going to turn out to be simply 3 centimeter. So this is why here I wrote that the beam segment has length 3 centimeter and it corresponds to a time interval of 100 picosecond. And again the average number of photons can be also can be calculated very easily in this 3 centimeter segment, that is going to be 3.1 into 10 to the power 9 divided by 3 into, because length segment is 3 centimeter, so you have I think it's easy to see that per unit length you are going to have 3.1 into 10 to the power 9 divided by 3 into 10 to the power 8 into 3 centimeter, which is 3 into 10 to the power minus 2 meter. So this gives you 3.1 divided by 10. That means on the average you are going to have simply 0.31. So I hope you are getting the maths, how I am getting the numbers. So if we consider now 10 such segments which has length 3 centimeter of the beam, okay, if we consider such 10 segments, most of the segments are going to be empty because the average number of photon is simply 0.31, and you may get a distribution of this type. Okay, you see most of the box here segment are 0, length segment are 0. For example, here you have only one photon in this segment, here there is no photon, and this all these you see segments are simply empty, and this means the average you can easily work it out. If you find out the sum, this sum is simply going to be 3, so it implies that mean is going to be 0.3. So
now I hope it is clear to you that the shorter the time interval, more difficult it is to know where the photons are. So in fact, thus, although the average photon flux can have a well-defined value, the photon number in the short time scale fluctuates due to the discrete nature of the photons. So this is a very important statement, and you see that the nature of the photon has this implication. Because of the discrete nature of the photons, you are having this fluctuation, and these fluctuations are described by the photon statistics of light. Now let us discuss or investigate the statistical nature of various types of light. First, let me consider a perfectly coherent light with a constant intensity, and we'll see that such light exhibits Poissonian photon statistics. Let us consider a light beam of constant power P, and its electric field is given by this expression. This electric field represents a monochromatic beam of light having amplitude E0, where its phase and amplitude E0 are constant in time. And you can actually consider the average number of photons within a beam segment of length L, which is given by the expression n bar, where n bar represents the mean number of photons in the beam and L is the length of the beam, then phi is the photon flux. So in terms of the photon flux, the mean number of photon is L by c, where c is the speed of light, into the photon flux. Now you see here we are assuming that L is large enough so that this mean value of photon number, that is n bar, takes a well defined integer value. Now subdivide L into n number of segments, and each of the segments having length L by n, and is assumed to be sufficiently large so that there is only a very small probability of finding a photon within a particular segment, and this probability of finding a photon in a particular segment is given by this expression, where n bar is the, as I said, it is the mean number of photons, and capital N is the total number of subsegments. Now the question is, what is the probability P of n of finding n photons within a beam of length L containing n number of subsegments? The answer is given by the probability of finding n subsegments containing one photon and n minus n number of segments containing no photons in any possible order. This is given by the binomial distribution, this as given in this expression here, where P, small p, is average number of photons, that means mean number of photons divided by total number of segments, subsegments, and we are considering the subsegment number to be sufficiently large, and we can actually work it out in the limit of very large n, that means n tends to infinity, capital N tends to infinity. You are going to get this expression here, and this expression represents the so-called Poissonian distribution. Let me actually show you how we can get this expression for Poissonian distribution. To do that, let me go the mathematical steps here. So we have the expression for the probability, that is given by this one, which I have already written, and this one I can rewrite in this particular form. And now I am going to look at various terms one by one. For example, first I look at this term followed by this particular term in the limit n tends to infinity. And while I do that, I am going to apply this formula, what is called the Stirling formula, which some of you may be familiar from your statistical mechanics course. This Stirling formula is that logarithm of n factorial in the limit capital N tends to infinity is n logarithm of n minus n, and using it, first I am considering this term, then I will consider this term. So first let me consider this term. here I have taken the logarithm of this term, and if I open it up, then as you can see, this is what I get inside the bracket here. And then if I open it up, now here if you look at these expressions carefully, this particular term and this particular term, because capital N is much larger than small n, these two terms get cancelled out. Similarly, this particular term n minus small n is we can just consider it to be n, then this term and this one get cancelled out. And similarly, this particular term and this particular term we can consider getting cancelled, and therefore nearly it is going to be equal to 0. So we get that in the limit n tends to infinity, this is what I get. Therefore in the limit n tends to infinity, this particular term in the expression for the probability can be considered to be equal to 1. Now let me consider this particular term, and here using this binomial expansion, I think all of you know, I can open it up, and in the limit n tends to infinity, you will see you are going to get this expression, and which is nothing but e to the power minus n bar. N bar is again the average number of photons or mean number of photons. So what you have obtained here is that this particular term in the limit n capital N tends to infinity is e to the power minus n bar, and utilizing this I can now write this expression. So here again I have written it here. As you can see, I can obtain the Poissonian distribution expression for the probability of photons. Now Poissonian distributions are uniquely characterized by their mean value n bar. To understand it, let me show you some representative plots. And here these are the plots. In these plots you can see that Poissonian distribution is plotted for beams of light having mean number of photons as say n bar is equal to 0.1, n bar is equal to 1. The various beams I am considering, 4 beams of light I am considering here. We are considering 4 beams of light having different values of mean number of photons. One is having mean number of photons as 0.1, another one is having mean number of photons is equal to 1, and then 5, and then 10. If you look at these plots carefully, you will see that the distribution peaks at the mean value n bar. For example, here you see n bar is equal to 0.1, the mean it is getting peaked at around 0.1. At n bar is equal to 5, it is again getting peaked at 5. For n bar is equal to 1, it is getting peaked at around at 1. And for 10, again as you can see, it is getting peaked at 10. I hope you are getting it. Also you see that the distribution gets broader. It's get broader as the mean value n bar increases. Now the fluctuation of a statistical distribution about its mean value are usually quantified by a quantity or a parameter called variance, and variance, as you know, is equal to the square of the standard deviation delta n, and it is defined as this expression. I'm sure most of you have seen this expression. So this is how variance is defined, and it is well known in Poissonian statistics that the variance is equal to the mean value n bar. So from here you see the variance is equal to mean value. It is in Poissonian statistics. It's a well-known result there. So therefore the standard deviation delta n is equal to simply the square root of the mean value n bar, and from here I can write delta n divided by, if I divide both sides by n bar, then here I will get root over n bar divided by n bar. So this gives me 1 divided by square root of n bar. So what it shows that it is very clear from this expression that the relative size is given by this one. Relative size of the fluctuation decreases as the mean value of the photon number gets increases, or as it goes on increasing, the fluctuation decreases. And it is also evident from the representative plots for the Poissonian distributions that we have shown here. As you can see, as the mean number of photons are increasing, the fluctuation is also getting decreased. Relative size of the fluctuation is also getting decreased. Now here at this stage, so this is important, relative size of the fluctuation decreases as the mean number of photons gets larger. Okay, at this stage I would like to mention and acknowledge that the discussion so far we are carrying out is based on the chapter 5 of this excellent textbook on quantum optics by Mark Fox. It is published by Oxford University Press. So far you learned that a perfectly coherent light that has a constant power shows Poissonian statistics, and photon number fluctuations satisfy this equation where delta n is the standard deviation and which is equal to square root of the mean number of photons. In fact, this equation provides us a benchmark for classifying other types of light according to the standard deviation of their photon number fluctuations. There are three possibilities. Say when the standard deviation delta n is less than the square root of the mean photon number, then such light is said to follow the so-called sub-Poissonian statistics. And on the other hand, when the mean photon number standard deviation delta n for the photon number fluctuation is greater than the square root of the mean photon number, then such kind of light are known to exhibit super Poissonian statistics. Difference between these three statistics, that is sub-Poissonian, Poissonian and super Poissonian statistics, is illustrated in this picture. Here you see this is a plot about the probability of finding n photons within a beam of light, and here the statistics are compared for lights having same mean photon number, that is here we are taking the photon number to be 100, and as you can see the distribution for the super Poissonian is broader than that of the Poissonian statistics, and that of the sub-Poissonian one is narrower than the Poissonian one. Okay, so in fact let me emphasize this fact once again, that a perfectly stable light having a constant intensity, that means whose intensity is not fluctuating with time, exhibits Poissonian statistics, right? So clearly all classical light beam which has a time varying light intensity is going to show super Poissonian statistics, because any classical fluctuation in the intensity we can expect to observe larger photon number fluctuation than the case with a constant intensity. For example, the so-called thermal light from a black body source has fluctuating light intensity and shows super Poissonian statistics. We are going to show it quantitatively very soon. Again, what about now the sub-Poissonian light when the photon number fluctuation has a narrower distribution than the Poissonian case? As you know that the perfectly coherent beam is the most stable light that can be achieved in classical optics, so it should be clear to you that sub-Poissonian light has no classical counterpart, and such light is completely non-classical. In fact, we are going to discuss it. We'll come to have a discussion about non-classical light later on. For now, let me discuss about the statistics of thermal light. You know that thermal light is the electromagnetic radiation emitted by a hot body, and it is also known as black body radiation. The properties of thermal light are generally understood by applying laws of statistical mechanics to the radiation within an enclosed cavity at a temperature, say T. The energy density rho omega d omega within the angular frequency range omega to omega plus d omega is given by this famous Planck's law, which you may have also seen in your first course on quantum mechanics. This is a very well-known formula. This is the Planck's law. Now you know that each mode of the radiation behaves like a harmonic oscillator. When we have quantized electromagnetic radiation, that is what we have learned, that each mode of the radiation behaves like a harmonic oscillator, and each mode has energy n plus half s cross omega. Now the probability that there will be n photons in a given mode of the thermal radiation is given by the so-called Boltzmann law, which maybe you have seen in your statistical mechanics course. So this is the probability distribution for thermal radiation. Now when we apply it for the quantized thermal light, which behaves like a harmonic oscillator each mode, then we just put En is equal to n plus half s cross omega. H bar is, again, let me tell you that it is a reduced Planck's constant, and h bar is equal to h divided by 2 pi, and here h is the Planck's constant. Now putting this En is equal to n plus half h bar omega in the expression for this probability distribution, here we obtain this expression. Then we can simplify it by just taking x is equal to e to the power minus s cross omega by kbt. By the way, kb is the Boltzmann's constant. Then it's simple mathematics to simplify this expression. I can now write it as x to the power n divided by summation x to the power n goes from 0 to infinity. And if you work out n is equal to this summation, if you work out in the denominator, so you are going to get, ultimately it would be 1 divided by 1 minus x. So this is what you are putting here, and from here the probability distribution for the thermal light can be written in this form. And this particular distribution is the so-called Bose-Einstein distribution. Please note that this is valid only for a single mode of the radiation field, and here we have taken the single mode to have a frequency omega. So this is the Bose-Einstein distribution, probability distribution, and using it we can find out the mean photon number in the thermal light, and this is easy to work out. Just I'm showing you the mathematical steps here. So I have this is n, and the probability distribution is going to give you the mean number. Then if I do the simple mathematics, just please look at it, it's very trivially it can be done. And finally, this is the simple expression you are going to get for the mean photon number. And if I put x is equal to e to the power minus s cross omega by kbt, and this one, and this can be rewritten in this familiar form. So this is the mean number of photons in a thermal light, and using it I can actually write x in terms of mean number also, and in that case I can write the probability distribution function for the thermal light in this particular form. The reason I am writing it in this form for the thermal light is that I can easily compare that with the coherent light which we have discussed, and you know that the coherent light its probability distribution obeys the so-called Poissonian statistics. And from these two expressions, as you can see, the probability distribution for the thermal light and the coherent light is expression wise also it is different. Now let me actually show you a plot comparing the photon statistics of thermal light and coherent light. So this is the plot. Here you see, if you see the plot carefully, as I have already told you that the thermal light follows the Bose-Einstein distribution. This is the distribution for the thermal light, and the coherent light obeys the Poissonian distribution. This plot depicts these two different lights. One is the coherent light and the thermal light for the same number, same mean number of photons, which is n bar is equal to 10. You can see that for Bose-Einstein's distribution, the thermal, the peak is always at n is equal to 0. As you can see, the peak is always at n is equal to 0, and then it decays exponentially. Also, the distribution of photon numbers for thermal light is much broader than that of the Poissonian light. In fact, we can show that for Bose-Einstein distribution, that is for thermal light, the variance of photon numbers delta n square is equal to n bar plus n bar square, where n bar is the mean photon number. And on the other hand, if you recall that for the coherent light or Poissonian distribution, the variance was equal to the mean photon number. So the variance of Bose-Einstein's distribution, that is for thermal light, it is always larger than that of the Poissonian distribution. So thermal light falls into the category of super Poissonian light. Now in the plot that I have shown, where we have taken the mean photon number to be equal to 10, and you can easily calculate and show that the standard deviation delta n for Poissonian distribution or coherent light is 3.2. On the other hand, for the thermal light, it is larger than that of the Poissonian distribution, and it is, if you calculate it, you will get it to be 10.5 for Bose-Einstein distribution.
Let me stop here for today. In this lecture, we have discussed about the photon statistics of a beam of light, and in this context, we discuss about the photon statistics of coherent light as well as thermal light, and we discuss about the three types of light which behaves three different statistics such as Poissonian statistics, sub-Poissonian statistics, and super Poissonian statistics. In the next lecture, we are going to continue our discussion on some of the statistical properties. Particularly, we are going to discuss about photon bunching and anti-bunching phenomena, and also we will discuss in somewhat details about coherent states of light. So see you in the next lecture. Thank you so much.